In this video, we're going to look at how to calculate equilibrium constants for a given chemical reaction. So often when dealing with equilibrium, you may be asked to calculate an equilibrium constant, either a Kc or Kp value for a given reaction. There's a few steps that you need to be aware of. The first step is that we have to determine the equilibrium concentrations for Kc or the equilibrium partial pressures when we're calculating Kp. Now, sometimes these may be given, which is very direct, or you may have to figure them out using the stoichiometry of the reaction, and we'll look at how to do that in a minute. So this step can be a little bit tricky. You have to be careful. Once you get the equilibrium concentrations or partial pressures, then it's pretty simple. You just have to write an equilibrium expression and then plug in your equilibrium concentrations or partial pressures and solve. To illustrate this, let's look at three problems. Take a look at this problem, read through it, pause the video, and try to solve this problem before I go over it. Pause the video. Okay, so the first thing I would do is let's set up what's called an ice table. An ice table helps us keep track of the concentrations or partial pressures when we're solving for a Kc value or Kp. An ice table stands for initial concentration, change in concentration, and equilibrium concentration, ICE. So here you have initial change in equilibrium concentrations or partial pressures, if that's what you're dealing with. And then up top, you have the species, the reactants, and the products for your chemical reaction. So now we have to plug in our values. We're given the volume and moles for each species. We have to insert these as concentration. So let's change them from moles to molarity by dividing the moles of each by the total volume. Now we have our molarity, and all of these are present at equilibrium, it says. So these are my equilibrium concentrations. So that was pretty simple. We now just have to write an equilibrium expression for this reaction. You can see that here. Again, be very careful that you remember to put your coefficients or express those as exponents. Then we just have to plug in our equilibrium concentrations and solve for Kc. You can see we get a value of 1.0 times 10 to the minus 5. Now you may say, why did we have to have a table with initial and changes in concentrations? For this problem, it wasn't necessary, but as you'll see, it can be very helpful to have those available. Let's look at a second problem. Read through this problem carefully, pause the video, and please give it a try before you look at the solution. Okay, so let's start out by writing our ice table in order to keep track of our concentrations, initial changes, and equilibrium. So we're given a few concentrations, or actually partial pressures in this case, but we treat those the same as concentrations. We're given the partial pressure of our N2O4 and our initial partial pressure of our NO2. Now again, these are initial concentrations, so we can plug those in under the initial concentrations blanks. We're also given one other value. We're given the equilibrium partial pressure of NO2. So let's plug that in. Now the next thing we need to do is let's figure out the changes in concentration. The changes in concentration, we need to use the reaction stoichiometry often to help us calculate the changes in concentration. So let's analyze this very carefully. Notice what's happening here. The initial concentration of my product is decreasing as it approaches equilibrium. So once it reaches equilibrium, we have had a decrease in concentration. You can see that. That tells us that the reaction is going from right to left in order to reach equilibrium. So our reaction is proceeding from products to the reactants. So our concentration of our products is going to decrease, that we see here, which means the concentration of my reactants must increase. How much will it increase? That's related to the stoichiometry. So we could say something like this. This decrease will be minus, because we can see it's decreasing here, minus 2x, and over here would be plus x. And again, that comes from our stoichiometry. For every 2 moles of this that react, we form 1 mole of this. Now for this problem, it might be easier to look at it slightly differently, and you'll see why in just a second. Instead of saying 2 moles to 1 mole, you could also say, just as correct, for every 1 mole of NO2 that reacts, we will form 1/2 mole of N2O4. You can see that, again, the stoichiometry here. And I do that because we know this X value. We know this X. The change is simply the 0.512 minus, or excuse me, 1.00 minus the 5.12. So we can get our change in concentration just by subtracting those two. So this is our change. And again, we must use our stoichiometry in order to figure out the change in concentration over here. For every 1 mole of this that decreases, we said we would form 1/2 mole of this. So our change over here will be half of what this is, but it will also be positive, again, because the reaction is going from right to left. So this one's a little trickier, but our change over here for N2O4, it's going to increase from its initial value by 0.244 atmospheres. So be sure you're clear on that stoichiometry and how we came up with that. Now we just add those two together. We add our initial plus the change in this case to get our equilibrium. So again, over here it's decreasing, so it must increase on the other side of the reaction. Now, once we got that, all we have to do is write our equilibrium expression, our Kp expression. Again, it doesn't matter that the reaction is going from right to left. As this reaction is written, whatever's on the left side, those are designated the reactants. Whatever's on the right side is designated as the product. Again, it doesn't matter which way the reaction is proceeding. My reactants are defined by what's on the left side, and what's on the right side defines what my products are. So that's important when writing your Kp or Kc expression. Again, it's always products over reactants. It's independent of which way the reaction is proceeding. So please make a note of that. Now finally, we just have to enter our partial pressures, our equilibrium partial pressures, and solve. And we get a value of 0.150. So that was a little trickier, but again, those are the types of problems we need to be able to solve. Let's try one last problem here. Read through this one carefully, pause the video, and see if you can solve for the Kc value. Okay, so now we have our chemical reaction. Let's set up our ice table to keep track of concentrations. We have we're given some initial data. We're told that we have a 1.10 molar PCl5 initial. We're not given any information about the other products, so we can assume those to be 0. Our concentration of PCl5 decreases to 0.33 molar at equilibrium. So we can tell that the reaction is going from left to right in this case because our reactants are decreasing. Our products are going to increase, therefore. So what's the relationship here? Well, look at your stoichiometry. For every 1 mole of this reactant PCl5 that decreases, we get 1 mole of PCl3 and 1 mole of Cl2. So our changes will be minus X over here, plus X and plus X. Again, everything's has a 1 coefficient because of the stoichiometry. Now we can figure out very easily what this X value is by subtracting 0.33 from 1.10, our initial. And we get a change, in this case a decrease, of 0.77 molar. So if X is 0.77, then we can fill that in here. And then our equilibrium, we just add that to our initial, which of course is 0. And boom, we have our equilibrium concentrations. So we just write our equilibrium expression, product over reactant, and we plug in our equilibrium concentrations, and we solve for Kc. And we get a value of 1.80. So again, practice some more of these problems and be sure you appreciate how to get those equilibrium values using stoichiometry. Sometimes it can be a little tricky. Once you get that, it's easy to solve for Kc or Kp.